Hey everybody, so these are the solutions to Worksheet 4.2. We're getting into graphing rational functions, which is sort of an extension of the last worksheet that we did in 4.1. So we'll be doing a lot of the same things, except here we're going to have a goal of actually sketching the graph ourselves rather than having to look and interpret the graph that we get from our graphing calculator. So the 6-step procedure sort of goes like this. So let's say we start off with f of x is equal to 1 over x squared plus 3x minus 10. First we're going to be asked to identify the domain. As before, we want to pick a domain such that any x values in our domain don't make the denominator equal to 0. So the way that we can ensure that that happens is we can say, well, here's our denominator, x squared plus 3x minus 10, and we want to make sure that this is not equal to 0. So we're going to find these zeros and then and exclude them from our domain. This one factors rather easily for us, so we're going to have x plus 5 times x minus 2, and that can't be equal to 0, which tells us that x plus 5 can't be 0 and x minus 2 can't be equal to 0. And what we were able to conclude from this is that in terms of the x values that we can choose for a domain, we cannot include -5 or +2. So these are our restrictions. So when it comes time to actually determining our domain, again, we can kind of visualize this first using a real number line that goes from infinity to -infinity, and we can first plot down the points that we don't want to include, 5 and 2. We'll put open circles there to show that we don't want to include them, and our solutions will, for our members of our domain, will be all of these points, just excluding 5 and -5 and 2. So in the end, our domain would be the interval from -infinity to -5. We're not going to include -5, and then from -5 to 2, and then from 2 to +infinity. So this, we'll close that off, and this would be our domain. Okay, so very similar to what we did last time. Next, we're asked to factor and reduce this if possible. So we've actually kind of already done the factoring, so we know that we've got f of x is equal to 1, so that sort of stays 1, and our denominator we determined factored as x plus 5 times x minus 2. So we look at this, there's really nothing to simplify, so we are done. So now we've got a rational function in its most simplified lowest terms. This is what we're going to work with for the rest of the problem. So for part C, we're asked to find any x-intercepts and any y-intercepts. Well, for x-intercepts, let's start with that. X-intercepts, the way that we want to do this is these are essentially the values of x that make our function equal to 0. A way to do this with rational functions, at least, is to go ahead and set the top equal to 0, the simplified top equal to 0, and solve for x. Now, if we do this in this particular case, what we end up getting is we get 1, and we set that equal to 0. Well, there is no x, and clearly this cannot be true. 1's not equal to 0, so what we have is we have no solution to this equation, which really all this tells us is that there are no x-intercepts in this case. So no x-intercepts. So our curve never actually hits the x-axis. So that's good to keep in mind as we get closer to our sketching step. Y-intercepts. So we've been doing this for a long time now. We know that the easiest way to find y-intercepts is to take our function and just evaluate it at x equals 0. It really doesn't matter whether you use the simplified or the unsimplified version. In this case, it's the same thing. So we'd go ahead and we could plug 0 in for x. So that'd be 1 divided by 0 squared plus 3 times 0, and then we'd have minus 10. So in the end, this reduces down to -1/10. So our y-intercept is going to be the point 0, -1/10. So that's another point that we can use to help get a good sketch of our curve later on. Okay, so part D. We're asked to find any vertical asymptotes and any holes. So let's revisit how we do this. For vertical asymptotes, I'm just going to abbreviate this VA. Remember, what we want to do is we want to take the simplified denominator. So after we factored it, if we cancel out any common factors, we want to take the simplified denominator, set it equal to 0, and solve for x. So in this case, our simplified denominator was x plus 5 times x minus 2. We didn't have to do any simplifications. So we set this equal to 0, and when we solve for x, we get our, in this case, 2 vertical asymptotes. So we're going to have vertical asymptotes at x equals negative 5 and at x equals positive 2. And these, coincidentally enough, are the 2 restrictions that we had on our domain. Now for the holes, remember that we find holes by, we look at to see if there are any common factors or common zeros between the original numerator and denominator before any simplification occurred. Now in this case, there were no common factors or common zeros. So no common factors between the top and bottom. So because of that, there are going to be no holes in this curve. So the implication here is no holes. Okay, so we're gathering little bits of evidence for our curve now. For part E, we're asked to find the horizontal asymptote if one exists, and then use that to sort of analyze the end behavior. Well, remember, with horizontal asymptotes, we want to pay attention to the degree of the top and the bottom. So if we go up to our function, the degree of this constant, so the degree here is going to be equal to 0. The degree here is going to be 2. So we've got a case where the degree of the denominator is greater than the degree of the numerator. In this case, what we're told in terms of the 3 possibilities, since the degree of the bottom, or the denominator, is greater than the degree of the top or the numerator, then this tells us that there exists a horizontal asymptote, abbreviated HA, at y equals 0. And this is always the case. So in the last worksheet, we had cases where the degrees were equal, and we took the ratio of lead coefficients. When the degree of the bottom is greater than the degree of the top, then this is where we always have a horizontal asymptote at y equals 0, which is essentially the x-axis. It's that horizontal line. So we can go ahead and conclude here that we've got a horizontal asymptote at the line y equals 0. Now in terms of relating this to end behavior in this particular problem, the way we talked about it last time is we could say that as our x values approach positive infinity, our function f of x is going to get closer and closer to a value of 0. And as x approaches negative infinity, our function f of x is going to approach a value of 0. It's going to approach this horizontal asymptote at the far ends of the x-axis. Okay, so we've got a lot of information already, but sometimes getting this sign chart together to determine where the curve falls above and below the x-axis is also helpful to get a good sketch. So we're going to go ahead and we're going to do that next. So when you put together your sign chart, the points you're going to want to include on this sign diagram, the ones you're going to want to plot, is really just the vertical asymptotes and any x-intercepts. Those will be the key points in determining where the curve is going to be positive or negative. So in this case, we don't have any x-intercepts, so we've just got to plot our 2 vertical asymptotes. So we could go ahead and we could set this up. So we'll start our sine diagram by taking the real number line from positive infinity to negative infinity, and we're going to drop down our two vertical asymptotes. So -5 and 2 are really the only 2 points we're going to write down. I'm going to mark this as that's a vertical asymptote and that's a vertical asymptote. The authors will sometimes use what's called an interrobang to represent this instead of writing VA, so you may see them write sort of the question mark with the exclamation point through it. It's totally up to you, whatever you'd like to use, but just make sure that you kind of know what's going on there. Okay, so once we've got our sine diagram labeled with the points of interest, we're going to go ahead and we're going to pick test points from each of these intervals, much like the way we solved quadratic inequalities. So we're going to go ahead and pick points. I'm just going to pick from this first interval, I'm going to pick -100, just a nice big negative number that falls in that interval. In the second interval, I'm going to pick 0 because that's really easy to work with. And then in this interval, I'm going to pick +100. Now what we're going to do next is we're going to test those points in our function, and we can use either the original simplified. In this case, it doesn't matter because they're the same thing. So we're going to use f of x is equal to, and I'm going to write it in factored form. And you could do this step a number of ways. This is just sort of the way that I like to think about it. Remember that we're not really interested in the specific value of these test points. We're really only interested in whether or not it comes back positive or negative. So when we're asked to evaluate f of -100, we could plug -100 in there and actually get a value and determine it's positive or negative. But especially since this is in factored form, I like to think about it in this way. So up top, we've got +1. That's always going to be a positive number. And we're going to take that positive number, and if we plugged in -100 for x, we'd have -100 plus 5, which would be a negative number. And then we'd have -100 minus 2, which would also be a negative number. So we've got a positive divided by a product of two negative numbers. So that's going to be a positive up top, positive below. So this is going to end up being a positive number. So we can mark this on our sine diagram as our function is going to be positive or above the x-axis on this interval. So I just think it's easier that way, and having this factored out really lends itself to this method. So let's go ahead and do it for the other two test points. So we could do f of 0, and again, if I plug in 0 for x, 1 will remain positive up top. If I plug in 0 for x, that's going to be a positive number for that first factor. If I plug in 0 for x with x minus 2, that's going to be a negative number. So I'm going to have a positive divided by a negative, which is going to give me a negative number. So in this interval, our curve is going to be negative or below the x-axis. And we'll do this lastly for +100. The top is always going to be positive since it's +1, a constant. Plug in 100 for each of the factors. The first factor will be positive. The second factor will also be positive. We're going to have a positive number over a positive number, which means we're going to have a positive result here. So our function will be positive on this interval. So again, we've got on this interval right here, our curve is going to be above the x-axis. On this interval, it's going to be below because it's negative, and then on this interval, it's going to be above. So this is all sort of in the hopes of us getting a good sketch. Okay, so let's actually do this. So we're going to get an accurate sketch without having to rely on our calculators here. So we'll start off by getting our axes set up. So this is y equals f of x, and then we'll have our x-axis right here. And let's just start sort of going back, take stock of what we found, and plot this on our curve. So if we go back, we know that we don't have any x-intercepts, but we do have a y-intercept at 0 and -1/10. So let's go ahead and put that down there. Let's say that this is -1. So we could plot our y-intercept right here. We'll just assume that's -1/10. It's going to be close, but that'll do. Okay, so we've got a y-intercept. There's 1 point. We could also go ahead and we could plot our vertical asymptotes at -5 and 2. So let's go ahead and mark those down. So we're going to have one over here at -5 and then one here at like positive 2. We could, if we wanted to, we could sort of mark them with these dotted lines so we know what's going on here, that they're going to be these sort of force fields that we can't cross. So what else do we know? There are no holes, so that doesn't help us, and we've got a horizontal asymptote along the x-axis, so we know that this is going to be our horizontal asymptote, just to kind of keep that in mind. We also know where our curve is going to be positive and negative, and we also know the end behavior. So let's start plotting this curve. So from negative infinity to negative 5, our curve is always above the x-axis, and it has to approach this horizontal asymptote of y equals 0 as it goes off to negative infinity. So the only real way to draw this would be something like this. So as the curve goes out to negative infinity, it's going to approach the x-axis, and as it approaches negative 5, it has to stay positive, so it's going to go shoot up to positive infinity. There really was no other option, especially since we know there are no x-intercepts on this. It has to stay up in that little corner right there. For the interval between negative 5 and positive 2, it's going to have to remain below the x-axis. There are no x-intercepts, so it's not going to touch it. The only thing that we do know is it's going to hit at this y-intercept right here. So I don't know exactly what it'll look like, but it should look something along the lines of this. It'll get close, then it'll hit it, and it's going to have to stay below the x-axis. So it might look like that. And then lastly, we know that on this last interval, as x goes off to infinity, it's going to have to approach our horizontal asymptote of y equals 0, and it has to stay above the x-axis. No x-intercepts. Can't cross that vertical asymptote either, so we're probably looking at something that would resemble this. So this should give us a pretty good sketch for our curve. Alright, so for number 2 on the worksheet, we are essentially doing the exact same thing. It's got a couple different things going on compared to the first one, but the process is really the same thing, and that's kind of what this worksheet's driving home, is there is a process, or that 6-step procedure to kind of get a good sketch of a rational function. Alright, so maybe we can go through this one with a little less wordiness, but it's the same type of process, like I said. Alright, so first thing we need to do, find the domain. Domain we take, we want to make sure that we don't get a 0 in the denominator. So we take our denominator, x squared minus 4x minus 21. We want to make sure that this is not equal to 0. If we had to, we could use a quadratic, but in this case it is it factors pretty nicely. So we're going to have x minus 7 times x plus 3 can't be equal to 0. So from this, we determine that if we don't want a 0 in our denominator, we cannot use x equals 7 or x equals negative 3. So those are the restrictions on our domain. We could see that pretty easily. If we sketch this out, we've got our slightly not quite straight real number line here, and we want to exclude negative 3. We want to exclude positive 7 here, so we don't include them. But we will take everything else into the domain of this function. So everything in between and then to the far ends of the x-axis. So our domain in interval notation would wind up being equal to the interval from negative infinity to negative 3, union with the interval from negative 3 to positive 7, union with the interval from 7 to positive infinity. So that would be the domain for this. So all real numbers except for those two, really. Okay, so next we need to factor and reduce, if possible, this function. So we know that we've got f of x, and the top, let's get up there so we can see it. The top is going to factor as x plus 5 times x plus 3. The denominator we've already determined factors as x minus 7 times x plus 3. And what we see here is that we have a common factor. So we can, these two factors will essentially become 1, and we can remove them from the formula, and our reduced function would be x plus 5 divided by x minus 7. Now this will be our simplified function, which we're going to use extensively, but we don't want to lose sight of the fact that we had that common factor. That'll be coming into play in a little bit here. But for now, this is our simplified rational function. Okay, so part C, we want to find any x or y intercepts. So if you remember from last time, the x-intercept we get by taking the simplified numerator. In this case, it's going to be x plus 5, setting it equal to 0 and solving for x. So what we get is we get x equals -5. So we're going to have an x-intercept at x equals -5. Moreover, it's going to be the point x equals -5, y equals 0. So that's the coordinate of our lone x-intercept here. And for the y-intercept, again, all we do is we take our function, we plug in 0. We could use the simplified or the non-simplified version. It's going to work either way. And we would have 0 plus 5 divided by 0 minus 7, which is going to give us -5/7. So the coordinate of our y-intercept is going to be x equals 0, y equals -5/7. So we've got 2 intercepts, so 2 points we can look forward to plotting on our curve. All right, so find any vertical asymptotes and holes. So for vertical asymptotes, again, we're pros at this now. What we're going to do is we're going to take our simplified denominator. We'll bring that into view so we can see that. The simplified denominator, which is x minus 7, we're going to set it equal to 0 and solve for x. So what we determine here is that we have a vertical asymptote at x equals +7. And then, if you remember for the holes, what we want to do is we want to note if there was a common factor in the top and bottom. Well, we did see that x plus 3 was a common factor back in part B here. So we would see that since x plus 3 is a common factor in the top and the bottom, then this is going to give away where we're going to identify the location of this hole in our curve. So the way we do this is we take that common factor, x plus 3, we set it equal to 0. This is going to give us the point x equals -3. So the hole in the graph occurs when x is equal to 3. We, though, want to find the y-coordinate for that as well. So to find the y-coordinate, we're just going to go ahead and we're going to calculate f of -3. And we're going to plug this into the simplified version. If we plug this into the original, we just end up getting 0 over 0. So we take -3 and plug it into our simplified function. We have -3 plus 5. And then we'd have -3 minus 7. This is going to give us, what, +2 over -10, or -1/5. So from this information, we realize that we have a hole in our curve at the point x equals -3, y equals -1/5. Okay, so now we can move on to the identification of our horizontal asymptote. Well, again, we're going to look at the degrees. Well, we can look at the degrees of either the original, so the degrees are 2 and 2, so the degrees are equal, or we could use a simplified one, and our degrees are 1 and 1 from part B. Either way, we see that degrees are equal. So we make note of this. So the degrees are equal. And this implies that we're going to take the ratio of the lead coefficients. So take the ratio of the lead coefficients of the top and the bottom. And again, in this case, we could use the simplified or non-simplified, and regardless, we're going to get the same one. The simplified one might be a better one to use just because it might be a little bit more straightforward. So we're going to have a horizontal asymptote at y is equal to the lead coefficient of the top, which is going to be 1, divided by the lead coefficient of the bottom, which in this case is also 1. So we can conclude that we have a horizontal asymptote at the line y equals 1. And again, if we wanted to interpret what this meant in the context of end behavior, we could say that as x approaches the end of the positive end of the real x-axis, that our function f of x will be approaching this value, positive 1. Similarly, as x approaches the negative end of the x-axis, our function is going to be getting closer and closer and closer to a value of positive 1. Okay, so we're getting there. So now we need to make a sign chart and plot additional points as needed. So let's go ahead and start this sign chart here. So we're going to get a real number line from positive infinity to negative infinity. And remember from last time we said what you want to go ahead and do is plot any vertical asymptotes or x-intercepts. If we go back and take stock, we've got an x-intercept at -5, and we have a vertical asymptote at +7. So we're going to drop both of those on here. So -5, this is a 0. And then +7, remember, was a vertical asymptote. Okay, so those are the only points we need to worry about. Now we're going to go ahead and pick test points. Kind of like last time, I'm going to pick -100 from this interval, 0 from this interval, and +100 from this interval. And we are just going to go ahead and plug these into our function. Now, I'm going to use the simplified version of our function here because this is going to be a lot easier to work through. You could use either, but this is going to be a lot easier. So if we take this and we start testing our points, well, we could start by plugging in -100. Well, again, we're really only interested in the sign here. Well, if I plug in -100 to the top, I'm going to get a negative number. If I plug -100 into the bottom, I'm going to get a negative number. So a negative over a negative will give me a positive. So my function is going to be positive. We're above the x-axis on that interval. Plug in 0. We're going to get a positive number in the top. We're going to get a negative number in the bottom. That means that on this particular interval that includes this test point 0, our function is going to be negative. We're below the x-axis. And for +100, we're going to have a positive up at the top, positive down at the bottom. And that means that our function will be positive. We're above the x-axis on this interval. So again, here it's above the x-axis. On this interval right here, it's below because it's negative. And then on this interval right here, it's above the x-axis. All right, so we have done a lot of work here. Let's see what we can do about getting a halfway decent sketch put together. So we'll start by getting our axes set up here. So here's our y-axis, and here is our x-axis. All right, so what did we determine? So we've got an x-intercept at -5, 0. So let's go ahead and put that there. So at -5, we've got an x-intercept. So I'm just going to put a nice point right there. We also determined that we have a y-intercept at -5/7. So not quite -1. I'll put a -1 here. And then we'll call this our y-intercept, -5/7. Close enough, right? Okay, so that helps. Next, we've got a vertical asymptote at 7. So if we go over here to +7, we can make note that we've got a vertical asymptote going on here. We can also take note from part D that there's a hole at -3, -1/5. So here at -3 and then -1/5, I'm going to put that -3 on the other side because I think it's going to get a little bit too close. So -1/5, it's going to be pretty close up here. I'm just going to put my open circle right there. That's about we'll call it negative 1/5. So that's a hole in our curve. And lastly, we've determined that there's a horizontal asymptote at y equals positive 1. So up here at positive 1, we know that we've got a horizontal asymptote. And now we can just use the information in terms of our sign chart to kind of fill in the rest of the blanks here. So from negative infinity to negative 5, it is going to be above the x-axis. And then it's going to go through this point. It's going to hit the y-axis at negative 5/7 and then stay below the x-axis all the way till positive 7. And then on the other side of positive 7 off to positive infinity, it's going to remain above the x-axis. So it should look something like this. Here's our asymptotic behavior from our horizontal asymptote. It's going to start dropping below the x-axis here. Let's try that again. All right, I'm going to start over. So hits right there, goes through, hits our hole, goes through the y-intercept, and now it's going to take a nosedive as it approaches this horizontal or this vertical asymptote. So we get something that kind of looks like that. And then up here, we'd have something that would look like this. So this is indicative of all of the information that we found. And I could probably be a little bit more clear on that's going to keep going down there. Okay, so this gives us a halfway decent sketch of our curve. Okay, so that's going to do it for this one. Lots of good stuff. Can be a little bit time consuming, but the good thing to know is that there is a process in sketching these. Okay, so thanks, and I'll see you all in the next video.